Reducing surface warming by increasing crop albedo. The potential for albedo to play an important role in global warming is clear from modeling of afforestation, deforestation, and indeed, increasing surface reflectivity has attracted considerably interest as another possible approach to mitigating the effects of global warming. In essence, the idea is very straightforward, as it involves increasing the albedo of surfaces that already reflect solar radiation back into outer space. The top surface of clouds and the upper surface of crop leaves have recently attracted interest as being of potential use in this approach. Before discussing a biological approach to this problem, we will briefly review the most recent geoengineering strategy for reducing surface temperature by increasing albedo. Low-altitude stratus clouds reflect a proportion of solar radiation back into space from their top surfaces. Cloud top albedo is controlled by, among other factors, reflectance from droplets of water in the clouds. Scientists propose to increase cloud top albedo by increasing the cloud droplet number, CDN, concentration. To do this, they suggest pumping a seawater aerosol into marine stratus clouds. Seeding with seawater particles will act to increase the number of cloud condensation nuclei from which the cloud droplets form. The overall effect will be to increase cloud top albedo by increasing the CDN and hence surface areas for reflectance. The scientists calculate that doubling the CDN concentration in all marine stratiform clouds will increase albedo by a value of 0.06, which in turn will produce cooling sufficient to roughly balance the warming associated with the doubling of the atmospheric concentration of CO2 from pre-industrial levels. Finally, scientists calculate that their proposed scheme has a capacity to hold the Earth's average temperature constant for another 100 years. The last technique is remediation of global environmental change by marine biota. About a third of the anthropogenic CO2 released to the atmosphere since 1750 has moved into the ocean. This is mainly accounted for by the solubility pump, increased partial pressure of CO2 in the atmosphere, causing more CO2 to dissolve in the ocean equilibration through the inorganic carbon system dissolves CO2, HCO3, and CO32 with increased pH in the surface ocean and ocean circulation. All these processes are affected by global warming. The present 0.1 unit decrease in pH, a 30% increase in the concentration of hydrogen ions from the value of 1750 will probably be a decrease of 0.5 units, a threefold increase in the concentration of hydrogen ions by 2100. The changes in surface ocean chemistry, called anthropogenic ocean acidification, have significantly biological effects. The most obvious of this is the decreased capacity of organisms to produce and retain skeletons based on calcium carbonate. Other effects include influence on photosynthetic inorganic carbon assimilation and on acid-base regulation, and as a consequence of these effects, changed biodiversity. Remediation of anthropogenic CO2 by ocean biota involves manipulation of the biological pump through photosynthetic primary productivity in the surface ocean, followed by sinking of the material to the deep ocean. Sinking of this organic carbon is essential in order to prevent immediate basoic metabolism back to CO2 near the surface, where it could exchange with the atmosphere. Sedimentation occurs by sinking of dense mineralized biota, and it is aided by aggregation and by association, at least near the coast, with mineral particles from the land. Primary productivity, and probably also the biological pump, is influenced by the changed surface ocean chemistry, as well as by changes in the surface ocean circulation resulting from global warming. This means that bioremediation is the ocean, as on land, must work in context with his continually changing environment. The availability of macronutrients such as nitrogen, phosphorus, and for diatom silicon, and the micronutrients iron are important constraints on marine primary productivity, which in turn can potentially increase the storage of inorganic carbon in the deep ocean. Supplying the nutrient elements that impose the greatest constraint on growth in a particular habitat could increase phytoplankton productivity. If this additional organic carbon sinks rather than being recycled at the surface ocean, there will be increased net organic carbon removal from the surface ocean and thus the atmosphere. Summarized data on the three main nutrient elements, nitrogen, phosphorus, and iron, that limit marine phytoplankton growth. The main conclusion to be arrived at from the research described in this review is that At present, biological approaches, just like geoengineering strategies, do not constitute a magic bullet capable of reversing the environmental changes brought about by increasing emissions of greenhouse gases. Without a doubt, what is needed is agreement and binding international legislation to reduce the emissions of CO2 and other greenhouse gases. However, given that this has not yet been achieved, the opportunity to buy some time using mitigatory approaches seem attractive. Accordingly, we shall examine what contribution the biological approaches described above might make towards environmental change mitigation. As previously discussed, strategies for soil sequestration, especially on degraded soils, have several potential advantages, including that they are likely to be cost-effective and bring additional benefits for soil fertility, and can be implemented almost immediately. However, on the basis of the currently available evidence, the capacity for soil sequestration to mitigate climate change is likely to be limited, and the loss of carbon from soil, for instance, caused by disturbance of climate change, is a major concern. Afforestation is at first inspection attractive. However, modeling reveals that extensive afforestation will only result in a limited impact on global warming over the next 50 years. Modeling suggests that increasing crop albedo could make a significant, although regional, contribution to mitigating the effects of increasing warming of surface air. However, it needs to be pointed out that this strategy will do nothing to counteract increasing atmospheric CO2 and its effects on ocean acidification. In this context, fertilization of the oceans to increase primarily productivity is currently attracting considerably interest. However, as described above, there are significant unknown, to the least of which is knowing whether the biota sink, and the presence of this unknown is sufficient to prevent the rapid implementation of this strategy.